I'm going to hit the record button, and then we can record this, and I can share this with you later if you are so inclined. Okay, so what I'm going to do, everyone, is whip through this rather quickly, and then I'm going to stop and pause in a couple of spots and give you a chance to write a couple things down, and then just know that there are certain items within chapters 1, 2, and 3 that I want to highlight. If we're lucky, I think we can get through this rather quickly, but you never know. I might get hung up and start talking, so we'll see. I'll try not to. So chapter 1 is just an introduction to environmental science. All of this stuff is pretty self-explanatory. One of the things that I do want to highlight on the environment, it's, we think of the environment sometimes as being this thing that's out there somewhere far away, like Yellowstone National Park. And really, for our purposes, we define the environment as being the place that we live, work, and play. So your environment for this class and for environmental science classes in your future includes your house, it includes your school, it includes this community in which you live, and then also, of course, wilderness areas and things that are outside. But really the environment refers to any place you work, live, or play. And the reason we want to expand that definition is because the places that you occupy on a daily basis, your environment, have an impact on your health, your well-being. So if we consider water, for example, we all consume water that comes from our house every day. So part of our job as environmental scientists is to examine all aspects of the environment, including things like the delivery system of that water, how does that water get to our homes before we consume it, etc. So I would encourage you to expand that definition beyond just perhaps like a definition that includes something that's outside and in the wilderness. These are terms that I think you have mostly experienced in your biology class, but again, when we refer to anything that is biotic, that's something that was living or is living now. And abiotic was never living. So the most obvious examples, I'm looking out the window, the biotic environment, the trees that I see, but also the logs that are laying in the forest that were once living. We also would consider those to be biotic. Abiotic would be like a rock, okay? And I'm going to keep on moving. One of the things about environmental science that I enjoy is it combines a lot of different areas of study and a lot of different interests. So I think I mentioned the first week, when you survey classes and you ask kids, well, what interests you about the environment? Some big items come out. There are some kids that love to hunt and fish. They love the outdoors. And so they're interested in environmental science because they love using the environment or the outdoors for recreation. There are some students that love the policy side of environmental science. So they get excited about politics. They get excited about things like the Paris Accord and the different components of that and how you go about creating policy. There's that side of environmental science. There's also the ecological side of environmental science. So there are students that will go into environmental science and their interest is researching the wolves of Yellowstone. How do the wolves of Yellowstone interact with all other parts of that ecosystem? And they're interested in the ecological side. So together, all of these things combine to form this study that we call environmental science or environmental studies. Humans manipulate the environment. We're going to see that time and time again, okay? Now, this is an important concept, okay? This is one that I do want to take a moment and just cover. And it's this word, environmental indicator. This is a word that I would highlight, I would write down, and I would encourage you to think about. This concept of an environmental indicator. So how do we know the health of the environment? How do we know the health of a particular specific ecosystem? How do you go about as an environmental scientist examining the components of an ecosystem to determine whether that ecosystem is healthy. And one of the indicators, or one of the ways that we can do that, is by examining various parts of that habitat, that ecosystem, or that larger scale thing that we're looking at. And if we break it down into pieces, some pieces tell us more than other pieces, okay? So if I go to a pond, all right, there are things that I can look for in a pond that will indicate the health of that pond. The presence of certain insect species indicates something about the condition of that pond. So that's a small scale example. We can also blow this up into larger scale examples, okay? So that's the concept of an environmental indicator. I'm going to give you an example of that, and we're going to go outside, and we're going to look at a detention pond this week. And we're going to look for very specific things when we visit that pond. Those specific things will indicate something about that body of water. This is another very important one, this concept of ecosystem services. When we think of the wilderness, or we think of nature, very commonly we conjure up these images of, we're hiking, we're fishing, we are out just enjoying the peaceful side of nature. Love doing that, no question about it. However, ecosystems also provide us with other services, and you can define and you can measure these services, okay? So one of the most common examples of this, which does require a little bit more digging, people will talk about the oxygen in our atmosphere. Where does the oxygen come from? How do we process carbon dioxide? And they will give the example of the rainforest and the service that the rainforest provides human beings, provides us with. They'll talk about this concept of clean air. So, we can think of ecosystems in this way, and we can actually, in some cases, measure the services that ecosystems are providing, okay? So these two concepts that you see on the screen right now, I want to explore these two concepts this week and apply them to an environmental issue that we have right here in Verona. You can look this page over. This page is an example of some indicators, and what they're using as an indicator are things like biological diversity. Okay, so the concept of diversity can indicate the health of an ecosystem. And in a second here, I'm going to show you a couple of examples of diversity. And then they're looking at other things here as examples like food production, surface temperature, carbon dioxide, the number of human beings on the planet, resource depletion, etc. Now, these are really big global indicators. In our class, we usually end up looking more at small scale indicators, but these are really big ones. Biological diversity, that's a big one, and I want to touch on that in a second here. Okay, so the rest of this slideshow goes through these big picture indicators, and I'm going to focus on biodiversity. If you take an environmental science class today, there are a couple of words that you hear over and over and over again. One is biodiversity, another one is sustainability, but biodiversity is one of the biggest ones. And so the reason biodiversity is important is it's a measure of the health of an ecosystem. And so when we examine an ecosystem, one of the things that environmental scientists will do, one of the first things they will do is they'll go in and they'll start to do a species count. They'll start to identify all of the different species that are present within an ecosystem, okay? And it's widely accepted that the more diverse an ecosystem, the healthier the ecosystem. So in a nice, vibrant, healthy ecosystem, what you expect to find are all of the levels of the food pyramid that you've been studying since, I don't know, probably third grade. And so you want to see producers, you want to see first level consumers that eat or survive on plants. You want to see second level consumers that eat the animals that eat the plants. And then at some point you want to get to the pinnacle of that food web or that, you know, food chain, and you want to see a large carnivore, and then that is an indicator of the health of that ecosystem. If you explore an ecosystem and you find one plant that dominates that ecosystem, okay, one plant, then that's going to impact all of the animal life that you see in the food chain above that level of producer, okay? And in general, when we end up with what is called a monoculture, or mono meaning one example of a dominant plant or a dominant animal, then biodiversity is low and the health of that ecosystem is generally low. Very commonly, those monoculture, either plants or animals, tend to be species that are invasive. So around Wisconsin, we talk a lot about this concept of native versus invasive. Native would be considered a plant or animal that exists naturally in the ecosystem or the habitat you're examining. And an invasive species would be a plant or an animal that has been introduced from somewhere else, another ecosystem. Now, Wisconsin, of course, we have to add a timestamp to that. You always have to add a timestamp because 20,000 years ago, if I was looking out my window, everybody, look out the window. Probably just looks like a really bright light, doesn't it? Okay, let's look out the window. Now, the light, it's a sunny day, so maybe all you'll see is, oh no, I think you can see some woods. Okay, 20,000 years ago, if I was looking out this window, what would I see? Anybody want to be brave and try to answer? You guys, you have no idea how weird it is to just talk to a bunch of initials. Here's the problem. I'm just going to keep talking. I'm just kidding you. Okay, 20,000 years ago, if I was sitting in this very spot, I look out the window. What do I see? A giant glacier. Could be a mile high wall of ice that extended all the way back to the North Pole. So obviously, if you're covered by a glacier, there is no native vegetation. That glacier melts or retreats, seeds start to blow in. Now you start to develop vegetation and ecosystems. And so this concept of native versus invasive, you have to put a timestamp on it. Okay, and in general, the timestamp that we like to use in this part of the world, about 200 years ago. And the reason for that is because that's when the European settlers arrived. We have a very strong bias toward European settlers. When we talk about the settlement of southern Wisconsin, people say, oh, southern Wisconsin was settled 200 years ago. Well, really, southern Wisconsin was settled probably at least 10,000 years ago. We know people have occupied southern Wisconsin for thousands of years, and maybe as long as 10,000 years. But the Europeans, when they settled Wisconsin, they changed the landscape in a very large way. The native or indigenous people to Wisconsin, by the way, also changed the landscape significantly. And we can talk more about that when we get into the spring and we do our prairie burn. But we know that the indigenous people started fires purposely in the landscape. And the reason for that was to maintain the prairies, maintain the open spaces, because in the open spaces in southern Wisconsin roamed the buffalo, also known as the bison. And it's much easier to support a family and a society on a mammal that weighs over 1,000 pounds than it is on a mammal that weighs 3 or 4 pounds like a squirrel. So they had a vested interest in maintaining the prairies. Okay, so how do we then examine this concept of biodiversity? We can look at biodiversity at a couple of different levels. One is ecosystem diversity. Consider southern Wisconsin. Consider Verona. Examine Verona within a 10-mile range of Verona, and we count how many different ecosystems appear in this locale. Okay, so just looking outside the window now, I see a pond ecosystem. I see an oak forest ecosystem. I see what will become our prairie ecosystem. We're in the process of building that now. So that's 3 different ecosystems right there. So you count the number of ecosystems. You can then get more specific on that. I could go to that oak forest that I just mentioned, that oak forest ecosystem, and I could count the number of individual species of trees, shrubs, herbaceous layer. I could count the number of squirrels, birds. I could start to break that down into species, and I would look at the diversity within that species or that ecosystem. And just for a quick example, when the old high school, we had a school forest, and the pond area in the school forest in 1999 was all reed canary grass. It was pure reed canary grass. There was not another plant growing in there, barely. And so I took a bulldozer and I scraped the whole entire pond area with a bulldozer. I scraped out 2 little ponds, and then I reseeded it with students. We seeded about 200 different species of plants. And if you go out there today, 20 plus years later, 21 years later, there's a lot of diversity. There are many different species of plants now growing. Very commonly in the springtime, you go out there and you can count up to 20, 25 different species of birds. And so that's how you increase diversity. You look at the number of species and you count the number of different species. Within each species, you can measure diversity by looking at the genetics, okay? And this is going to be a very important topic when we get to somewhere around chapter 7 or 8. So within the chipmunk population, there are going to be variations. Those variations are embedded within the genetic code, okay? And you can actually examine that genetic code and see how diverse that group of chipmunks are. And we'll talk more about how chipmunk populations become diverse. Okay, so that pretty much takes care of that. There is one thing here that I would like to just focus on and highlight, and that's called the background extinction rate, okay? This is important, everybody, because it's normal on planet Earth, every single year, it's normal for certain species to go extinct, okay? Evolution, there's competition for resources, and some species just die. Some species do not make it. This has been happening for as long as life has been present on our planet. It's called the background extinction rate. So in a normal year, you would expect as a scientist for a certain number of species to just disappear from the planet. The reason that's important is because if you have an understanding based on the fossil record of how many species normally disappear in a given year, then you can use that as a way to measure the health of our planet. Right now, most scientists believe that we are in what is called a mass extinction period. And so the number of species that you would normally expect to disappear is not happening. Instead, we have many, many times the number of species disappearing. That should sound some alarm bells. What's happening? Why are so many species today going extinct? If you look at the fossil record, there's some debate over this. Some evolutionary biologists would argue we've had 5 mass extinctions. Some say 6. Some say we are in one right now. But you can go in the fossil record and you can measure the number of species that have disappeared over time. And there are periods when we've had all of a sudden a whole bunch of species die off. What are the implications for that for the health of our planet? Okay, that's about it, everybody. I'm going to go ahead and whip through the rest of this and call us done. Okay, that is chapter 1. I know, it was fast. Okay, now I'm going to close this up. If I can find my mouse. And so chapter 2, where is the little mouse thing here? Okay. Chapter 2, we can go through really quickly. Chapter 2 covers a lot of chemical stuff and power, and this is stuff that you can certainly review, but it's not stuff that we're going to be tested a whole lot on. Although I will say the law of thermodynamics, you should remember the law of thermodynamics. Let's just hit this quickly. So basically, it's this idea that energy is never created nor destroyed. So the amount of energy in the universe is constant. You can't create energy and you can't destroy energy. It's always the same amount, no matter what. You could also apply this to conservation of mass or matter. The same law applies to those concepts. The amount of matter in the universe is constant. Nothing's ever created or destroyed. It just changes forms, okay? So that's the first law of thermodynamics, and we're going to see why this is important when we look at cycles. The second law is a kind of a practical application of it, and that basically states that you're not creating or destroying energy, but when you transfer that energy, what we might call use the energy, some of it is diminished in terms of the amount of work that can be done. So we will say things like, I'm using energy when I turn on the lights, okay? But the law of thermodynamics states that you can't create or use energy. You can't destroy it. So it's true, I'm not destroying the energy when I turn on the lights. I'm using the energy. It's changing form, okay, from electrical energy to light energy. And it's there still somewhere, but the usefulness of it is reduced. That's the second law of thermodynamics. And the idea behind it is really it's just more practical, okay? It just says that, hey, it's not destroyed, but it's not there for us to use. So in the example that you see on the screen, we're producing electricity at a power plant. We're converting coal or natural gas. We're breaking those bonds. Those bonds ultimately came from the sun, photosynthesis, plant material. Plant material turns into coal. We break those bonds. We turn it into electricity. And then we use the electricity. Some of the electricity is given off as heat, and we can't use it for anything else. So really, this chapter is mostly just review of physical science, and you can whip through it really quickly. I would put a highlight around open systems and closed systems. And the idea with an open and closed system is it relates to the inputs and the outputs. So if you consider planet Earth in terms of energy, we get energy on our planet from outside of the system, the sun, right? And we radiate energy into space. We have outputs. So that's not a closed system. That would be considered an open system in terms of energy. However, matter, we're not throwing things out into space, solid objects, although we do occasionally get some input in the form of meteorites and things. But for the most part, in terms of matter, our system is closed. All of the matter that's on our planet is recycled, but we don't add or reduce it. The feedback loops will probably hit a different time. So really that's really just the key with that chapter. Again, real fast, there's not much in there. This one, maybe we just end with this today. This concept of feedback loops is important because in nature, we see this happen. And we're seeing this happen pretty dramatically right now in relation to global warming. So I'll give you an example of that now. So there are negative feedback loops and there are positive feedback loops. A negative feedback loop, there's something that happens that there's a consequence of that first action, okay? And the consequence eventually leads to the original thing being reduced, okay? So a negative feedback loop, the example here, what do we have? We have a lake level, okay? We have lake level. So the idea is that if you have a surface area and you reduce the surface area, there's less surface area, less water to evaporate. the less evaporation causes the lake level to rise. Okay, but then that leads to more evaporation, okay? And then the lake level is going to drop, which reduces the surface area, less evaporation, lake level rises. So it's a loop that doesn't get out of control. A positive feedback loop is a loop that can eventually spiral out of control. So this example is birth. So if you have an increase in population, more people, more births leads to more population. Now you have more people, which means you're going to have more births, and the population just keeps spiraling out of control. Let's just quickly apply this to global warming. So you probably have heard how the Arctic is melting, the ice caps are melting. Well, the ice caps have a very high reflectivity. It's called the albedo. It's a measure of how reflective the surface is. And so this is another example of a positive feedback loop. The temperature warms, that melts the ice. But if you melt the ice, less of the solar radiation that's coming from the sun is reflected into space. So more goes into heating the earth, which melts more ice. But if you melt more ice, then even less radiation is reflected. It warms the planet even more, which melts more ice. So it's a feedback loop that causes the initial phenomenon to continue to increase. So it's important to understand that and to kind of, I mean, it's something that we are going to talk about in particular around global warming. Okay, now that, everybody, is how you have the, wait a minute.